Jnanam Paramam Dheyam. Knowledge is supreme.
So welcome to this lecture on Advanced Transition Metal Organometallic Chemistry. Today's is the second lecture. In our first lecture, we had briefly spoken about various kinds of allyl and aniline ligands offer a wide range of electron donating capacities in terms of electrons that they donate while binding to transition metals. And this range can go from 2 electron donor to about 8 electron donor. Another interesting feature about this allyl and enyl ligands is the fact that these ligands can bind in neutral, anionic and cationic forms. Now, ligand binding to metal in neutral and anionic form, however, ligand binding to metal in a cationic form is kind of counterintuitive. The reason being, ligands are supposedly thought of as something which is electron rich, whereas metals are supposedly thought of something which are electron deficient. So the metal ligand interaction is an interaction that involves electron rich species with that of an electron deficient species. Now, cationic ligand in this context is kind of counterintuitive. Now, being cationic, the ligand no longer can be thought of as something which is electron rich, and hence it is kind of not so easy to conceive the fact that how cationic ligands bind to transition metals. Now, one of the versatility of these allyl and enyl ligands is the fact that they can bind both in radical, anionic and cationic forms. In our last lecture, we have also looked at the transition metal allyl and enyl ligand interaction. And what we saw is that it contains two kinds of ligand to transition metal sigma and pi interactions. Sigma interaction as well as ligand to transition metal pi type interaction, and lastly there is also a transition metal to ligand interaction which is of pi type, and they are called as back donation, because the obvious donation of electron density happens from ligand to metal, and in back donation there is a reversal of donation that occurs from transition metal onto ligand. Now, these three interactions constitute this transition metal allyl interaction. We have discussed this in our previous lecture, and these forward donation, the first two are called forward donation, and the second one is the third one is called backward donation. These two interaction sort of define transition metal allyl ligands or ligand bond. Now, with that said, in this lecture what we intend to do is to look at various preparative methods which are out there for preparing these transition metal allyl complexes. Now, obviously, there are several methods which are available for synthesizing these transition metal allyl type complexes, and depending on the nature of the synthesis, these preparative methods can be classified into 3 classes or subclasses. So, this preparation of transition metal allyl complexes can be classified into 3 subclasses, and first one is replacement of an halide on a metal by an allyl moiety or allyl anion. So, this is similar to salt metathesis exchange, where there is a halide on the metal precursor and the allyl anion goes and replaces the halide, resulting in transition metal allyl bond. The second method is a rearrangement reaction of eta 1 bound sigma allyl bond to a pi bound eta 3 bound pi allyl bond. So, over here the hapticity changes from eta 1 to eta 3, and as a result a sigma allyl ligand become a pi allyl ligand. We will take a look at various examples which belongs to this category. Now, the third one is a conversion of pi olefin. Now, olefin usually is bound in a eta 2 or eta 4 fashion to a pi allyl ligand, which is bound in a eta 3 fashion. So, to summarize, what we see is that there are various methods available for the synthesis of transition metal allyl complexes, and all of these methods can be further classified into 3 main types of preparations. First of all, being a simple replacement of a halide anion on the metal precursor by an allyl anion, and the second one is a rearrangement of a allyl moiety from eta 1 bound sigma allyl ligand to a eta 3 bound pi allyl ligand, and third one is a conversion of pi olefin ligand which are bound eta 2 or eta 4 to the transition metal to an pi allyl ligand which is an eta 3 bound. These are the 3 sub classes of methods which are available for preparation of transition metal allyl complexes. Now, let us look at these subclasses, individual subclasses in much more details. The first one, obviously, as I said, is a reaction of metal salt plus main group organometallics. This reaction is popularly called as a metathesis reaction. For example, nickel bromide reacting with two equivalents of allyl magnesium bromide in ether at low temperature minus 10 degree centigrade produces nickel bis allyl. Similarly, cobalt acetyl acetonate thrice reacting with three equivalents of allyl magnesium bromide produces cobalt tris allyl. Now, this compound is highly unstable and its decomposition temperature is above minus 55 degrees centigrade. So, in order to stabilize this cobalt tris allyl compound, one has to be or attain a temperature range below minus 55 degrees centigrade. Similarly, zirconium tetrachloride reacting with four equivalents of allyl magnesium bromide, magnesium chloride, again in ether at minus 78 degrees centigrade produces zirconium tetraallyl complex. Now, one important features which stands out is the utility of a Grignard reagent in these metathesis reactions. And second thing that stands out is that this method represents a very general method for synthesizing binary allyl complex. General route to binary allyl complexes. Now, these binary allyl complexes are also called homoleptic complexes because they are made of one kind of ligand. If a transition metal organometallic compound is made of two different kinds of ligand or more than one different types of ligand, these can also be referred to as being heteroleptic complexes. So, over here transition metal binary allyl complexes can be synthesized very easily using this general route. Now, one interesting thing about organometallic compound, particularly with respect to binary allyl complex, is that these complexes are supposedly very reactive, and this reactivity is primarily due to their kinetic lability rather than that of thermodynamic origin. And from that perspective, preparation of pure binary allyl complexes or any binary homoleptic organometallic complexes remains a challenge, and from that perspective this particular route which exclusively gives binary allyl complex is of particular importance. Now, as mentioned that these binary allyl compounds are extremely reactive, and because of this reason the synthesis and isolation are to be done at low temperature. requires low temperature, as these ligands are thermolabile. So, now let us look at the next method available for synthesizing these transition metal allyl complexes, and this particular method involves reaction of a carbonyl metallate anion with allyl halide. So, the reaction is given as five plus C5H5Cl giving allyl MnCO5, which is eta 1, and this losing a carbon monoxide giving eta 3 MnCO4. In the earlier reaction where allyl Grignard was used, the allyl ligand was used in its anionic form, whereas when allyl chloride is being used in this reaction, then the allyl moiety is used in its partially electron deficient or cationic form, because chlorine being more electronegative, the carbon bound to the chlorine will be del positively in the charge. And from that perspective, for these reactions to happen, one needs to have a metal species which is highly electron rich, and this can be attained none other than with this metallate anion. So, in metallate anion there is a sodium positively charged sodium bound to MnCO5 minus. So, metal is really electron rich, and hence it attacks this allyl chloride, giving rise to eta 1 allyl MnCO5 that subsequently loses a carbon monoxide, resulting in eta 3 MnCO4 allyl complex. So, here we see an example of the second method that we spoke, which involved a rearrangement of eta 1 to eta 3 allyl moiety. So, the second example of this also involves a reaction, another reaction of a CP tricarbonyl molybdate anion. So, again this is a metallate, this reacts with benzyl chloride, loses a chlorine to give a eta bound molybdenum alkyl complex, which loses carbon monoxide to give eta 3 bound allyl complex. So this is an allyl pi complex of benzyl anion, and so over here it is eta 3, over here it is eta 1, and this sigma pi rearrangement, this is called a sigma pi rearrangement, takes place with the loss of CO and can be initiated photochemically as has been done over here with this light, or even thermally. Now this photochemical dissociation of carbon monoxide as well as thermal dissociation of carbon monoxide at elevated temperatures have been reported or are known for a long time, and such can be systematically utilized in preparation of eta 3 allyl complexes from eta 1 allyl complex using this sigma pi rearrangement reaction. The another example of this metal allyl complex synthesis involves the reaction of metal carbonyls with allyl halide. For example, reaction of Cp cobalt dicarbonyl with allyl iodide gives this cationic Cp cobalt allyl carbonyl compound with an iodide anion plus a neutral Cp cobalt allyl iodide. To note that these two, both the species are 18 electron compounds. For example, 5 from Cp, 9 from cobalt, 2 from carbonyl and 3 from allyl, this resulting in and a cationic charge to that, so resulting in overall 18 valence electron compound. The same counting can be done for the other compound, 5 for Cp, 9 for cobalt, 1 for iodide and 3. So this also gives in 18 electron valence electron compound. So the other method for preparation of transition metal allyl complexes is from the transition metal olefin compounds. This is the example which belongs to the third category, and that starts with the reaction of a metal hydride with diolefin. cobalt tetracarbonyl hydride reacting with butadiene loses a carbonyl to give this allyl cobalt tricarbonyl a mixture of this isomer. This one is anti and the other one is syn. This reaction proceeds via the transition state, which involves this cobalt hydride adding against this conjugated double bond, and the transition state thus is tetracarbonyl cobalt methyl complex, which then subsequently loses a carbon monoxide to give these syn anti isomers. Of the two, the syn, as seen from the geometry, the syn isomer is more stable. So, with this I come to the end of today's lecture, in which we have spoken about various methods which are available for preparation of transition metal allyl complexes. Now, the methods that are available, they all can be classified into three subgroups. One is simple metathesis type, where a metal precursor halide is replaced with a allyl anion. The second one is a transition metal allyls eta 1 bound sigma allyl complex rearranging to transition metal bound eta 3 allyl complex, and the third one is a conversion of transition metal bound olefin complex to a transition metal allyl complex. Now, for the first examples, it is very simple. It is simple metathesis of metal halide precursors with allyl anions. These are usually derived from Grignards like allyl magnesium bromide and chloride, and this method is a very useful method for preparing the challenging transition metal binary allyl complexes. These homoleptic transition metal organometallic complexes are extremely reactive and difficult to synthesize. From that perspective, this metathesis reaction producing binary transition metal allyl complex is noteworthy, and one has to be aware of the fact that these compounds are unstable, and hence the synthesis and isolation of this transition metal allyl complex have to be undertaken at a very low temperature. Now, the second method, the sub method involved conversion of sigma transition metal sigma allyl complex to eta 3 bound transition metal allyl complex. These reactions primarily involve formation of these compounds from transition metallate complexes with allyl halides, and subsequently a decoordination of carbon monoxide resulting in eta 3 bound transition metal allyl complex. So, there are two or three different methods which utilizes the same principle, where eta bound sigma allyl complex is converted to eta 3 bound transition metal allyl complex. And lastly, the third subclass involved the conversion reaction of transition metal hydride with diolefins, and in the process generating eta 3 bound allyl complexes. The reaction that we have looked at is cobalt hydride tetracarbonyl reacting with butadiene, giving a mixture of syn and anti isomer of allyl cobalt tricarbonyl compounds, and of the two syn and anti-isomer, the syn isomer is more stable than the other isomer. So with this, I conclude today's discussion on transition metal allyl complexes. As for today, some more of the preparative methods still remains, and which will be the subject of discussion in the next lecture. And we are going to also look at the reactivity of this kind of transition metal allyl complexes before we move on to other enyl ligands. So with that, thank you for being patiently listening to this lecture, and I look forward to taking up this topic in more details when we meet soon. Thank you.